Welcome back to the Deep Dive. Today we're jumping into something pretty fascinating, a problem right at the crossroads of quantum physics and pure math.
Yeah, and it's a problem that got so tricky, so notoriously difficult, that one mathematician actually bet 10 martinis on finding the solution.
10 martinis. That's quite the prize. So our mission today is to unpack that story. How does this incredibly complex math proof connect the messy reality of electrons buzzing around in a magnet
To the, perfect, infinitely detailed world of fractals and number theory? It sounds completely separate, doesn't it?
It really does. We're basically looking at how a specific version of the Schrödinger equation, the bedrock of quantum mechanics, led to this hidden pattern.
Right, the Hofstadter butterfly. It dictates the energy levels an electron is allowed to have when it's in a crystal grid near a magnet.
And solving that equation for those energy levels, that was the thing causing headaches back in 1974.
Oh, big time. A whole group of really smart theoretical physicists were tearing their hair out over it. They had the equation, sure, but actually solving it for, the really complex, messy situations. That was the wall they hit.
Okay, so enter Douglas Hofstadter.
Exactly. This is Regensburg, Germany. Hofstadter's there. He's a graduate student. This is actually 5 years before his super famous book, Gödel, Escher, Bach.
Right. So he wasn't famous yet.
Not at all. And he joins this group of theorists, but he admitted later he couldn't quite follow their very abstract thinking.
And that turned out to be a good thing.
Surprisingly, yes. Because he wasn't locked into their way of thinking, he sort of stepped back. He decided to treat it almost like a visual puzzle.
Instead of proving theorems, he went hands-on.
Totally. He called it a down-to-earth approach, which for him meant grabbing this enormous HP 9820A desk calculator, weighed 40 pounds apparently.
40 pounds. Okay, so not exactly a laptop. And what did he do with this beast?
He started feeding it numbers. Specifically, he was focused on this key variable in the equation called alpha.
Alpha. Okay, what does alpha represent?
It basically bundles up the effect of the magnetic field on the electron. It's related to the field's strength and the actual size of the little squares in the crystal grid the electron is moving through.
Got it. And here's where the path splits, mathematically speaking.
Precisely. The physicists, they already knew that if alpha was a rational number, a simple fraction like 12 or 34, or a whole number, the equation was, hard, but you could eventually solve it. Tedious, but possible.
But the real world isn't always simple fractions.
Exactly. The killer case, the one they couldn't crack, was when alpha was irrational, like pi, or the square root of 2, numbers that just go on forever without repeating.
For those numbers, they had nothing.
No method, no way to figure out the electron's loud energies. It was a complete mathematical roadblock.
So Hofstadter, with his calculator, he couldn't input irrational numbers directly.
Right. Calculators can't handle true irrationals, but he could put in loads and loads of rational numbers, fractions, thousands of them.
And what was the calculator actually calculating?
It was churning out the energy levels. For each fraction he fed in for alpha, it would calculate which energy levels were allowed for the electron and which were forbidden. It would just whir away all night sometimes.
I just picture this scene. Him hunched over this giant machine, paper scrolling out.
Yeah, huge scrolls of graph paper taped together.
While the theorists are doing their high-level abstract stuff, what did they think?
Oh, they mostly dismissed him. They actually nicknamed the calculator Rumpelstiltskin.
Rumpelstiltskin, like the fairy tale.
Yeah, joking that he was trying to spin computational straw into theoretical gold. His own advisor apparently called it numerology, just messing with numbers.
Ouch. But it wasn't just numerology, was it?
Not even close.
Yeah.
Because when he took all that output, all those allowed and forbidden energies for different fractions, and painstakingly plotted them on his taped-together graph paper,
A pattern emerged.
Something totally unexpected. He later said it was like catching a tiger by the tail.
And this visual result, this graph, this is the Hofstadter butterfly.
That's the one. It got its name because the gaps on the graph, the forbidden energy zones, looked remarkably like the intricate patterns on a butterfly's wings.
So the structure wasn't in the allowed energies, but in the forbidden ones.
Kind of both. But the pattern of the gaps was really striking. He noticed something key. When he used a simple fraction for alpha, you'd get some breaks, some forbidden zones.
Okay.
But as the fractions got more complex, like 35 versus 2971 or something, the number of drakes, the number of forbidden gaps just exploded. It created this incredibly detailed, fractal pattern.
Fractal, meaning?
Meaning it had self-similarity. Little parts of the pattern looked like the whole thing just scaled down. infinite detail packed into a finite space.
Wow. And this wasn't just some random new pattern.
No. And this is the amazing insight. Hofstadter recognized it. He realized this fractal structure looked exactly like something mathematicians already knew about. The Cantor set.
The Cantor set. I vaguely remember that. You start with a line.
Exactly. Georg Cantor described it back in 1883. You take a line segment, erase the middle third. Then you take the two remaining segments, erase the middle third of each of them.
And you just keep doing that.
Infinitely. You repeat the process forever. What you're left with isn't solid lines, but this infinite collection of points, like mathematical dust scattered across where the line used to be.
So what does it mean for the electron's energy levels to form a Cantor set?
It means the possible energies aren't continuous bands with maybe a few gaps. Instead, there's an infinite number of forbidden energies, these gaps within gaps within gaps, spread out like that Cantor dust.
So an electron in that situation would have an infinite number of energies it just couldn't have.
Precisely. It implies this incredibly complex, structured quantization, a blend of ultimate structure and, in a way, ultimate uncertainty about where the energy can be.
Okay, so Hofstadter sees this visual pattern, connects it to the Cantor set. All from his numerology. What was his next step? A guess.
Basically, yeah, a visually driven hypothesis. He reasoned that as the rational fractions he could calculate got closer and closer to a true irrational number, the case nobody could solve, the energy structure looked more and more like a Cantor set.
So he leaped to the conclusion.
He hypothesized that when alpha is truly irrational, the set of allowed energies wouldn't just look like a Cantor set. It would be a mathematically perfect Cantor set.
That's a huge leap based on a graph from a calculator.
Incredible intuition. But, a picture isn't a proof. The theorists needed to catch up.
How did they approach it? Did they pick up on his visual work?
They came at it from a different angle, more about the dynamics of the system. This brought in mathematicians Barry Simon and Mark Kiltech. They had a key insight.
Which was?
They realized that when alpha is irrational, the underlying math of the Schrödinger equation changes. It becomes something called an almost periodic function.
Almost periodic, meaning it nearly repeats but doesn't quite.
Exactly. Think of a path that loops around, comes incredibly close to where it started, but never perfectly retraces its steps. It has that kind of infinite non-repeating complexity you see in fractals.
Ah, okay. So that connects back to the fractal idea.
Right. And based on their expertise with these strange, almost periodic functions, Simon and Caddick looked at Hofstadter's conjecture and said, yeah, he's probably right. It should be a Cantor set.
Probably right. Doesn't sound like a proof either.
Nope. Agreeing isn't proving. So in 1981, Mark Caddick famously made the offer. He said, okay, I bet 10 martinis to whoever can actually prove this.
And the 10 Martini conjecture was born. Did Caddick get to pay up?
Tragically, no. He passed away in 1984, well before the proof was found.
Oh, that's sad. How long did it take?
It took a while,
Right.
until 2005, actually. Two mathematicians, Svetlana Judomirskaya and Artur Avila, finally published a proof. Avila later won a Fields Medal, partly for this work.
The Fields Medal. Wow, okay, so a major achievement. And did they get the martinis?
They did. Apparently, they honored the spirit of the bet and collected.
Ah, that's great. But you mentioned this first proof. It wasn't the end of the story. There was a limitation.
Right. This is where the next phase begins. While crucial, that 2005 proof was often described as a patchwork quilt.
Patchwork quilt, meaning it wasn't elegant.
It means it wasn't one single unified argument. They had to use different mathematical tools and techniques for different scenarios, different ranges of the parameters.
Like sewing different pieces of fabric together.
Exactly. And importantly, it relied on some simplifying assumptions about the physics, like maybe the magnetic field was perfectly uniform or the crystal grid was perfectly simple.
So it proved the butterfly existed in a kind of idealized mathematical world.
Pretty much. It confirmed Hofstadter's intuition for a specific, simplified model. But it left open the question, was this beautiful fractal just a mathematical curiosity, an artifact of the simplified math, or did it actually describe reality?
And people were skeptical, even Hofstadter himself.
Yeah, there was a lot of doubt for decades. Hofstadter even wrote in Gödel, Escher, Bach, something like, if an experiment ever actually saw this butterfly structure, he'd be the most surprised person in the world.
He thought it was just a feature of the math, not the physics.
That was the strong implication.
Yeah.
That maybe the complexities of the real world would just wash it all out.
Which makes what happened in 2013 even more dramatic.
Absolutely.
Yeah.
A huge turning point. This is when the experimentalists shock everyone.
What did they do?
A physics group at Columbia University. They did this incredibly precise experiment using graphene.
Graphene, that super thin carbon material, right? 2 layers of it.
Exactly. 2 atomically thin layers placed in a strong magnetic field. They weren't just looking at overall energy levels. They were carefully measuring how electrons behaved, their conductivity, essentially.
And they found, don't tell me.
They found it. Clear as day in their experimental data emerged the Hofstadter butterfly. All the intricate fractal structure, the gaps within gaps, it was right there.
Wow. Just wow. After decades of being a mathematical picture, suddenly it's showing up in a real lab, in a real material.
You can imagine the reaction. It completely flipped the script. The butterfly wasn't just an abstract idea anymore. It was a real-life phenomenon, as Jitamirskaya put it.
That must have been unsettling, like you said.
Yeah, very unsettling was her word, because it proved this incredibly abstract number theory, dealing with irrational numbers and fractals, had real predictive power about the physical world.
And it put pressure back on the mathematicians.
Definitely. It basically said, okay, your patchwork proof was nice, but reality seems to follow this pattern more generally. We need a better explanation, a unified one.
So the goal became finding a single proof, not a quilt, that could explain why this butterfly shows up in real experiments, not just simplified models.
That was the new holy grail.
Yeah.
Moving beyond the specific case to a general theory.
And this leads to the global theory idea from Artur Avila.
Yes. Avila had been working on this broader concept. The goal of a global theory is kind of like finding a master key, instead of fiddling with lots of different tools.
You find one unifying principle.
Exactly. He was developing this idea of associating a specific geometric object with a whole class of these almost periodic functions, like the one in the Ten Martini Problem. The hope was, if you understood the geometry of this object, you could understand the solutions to all the related equations.
A high-level structure connecting everything.
That was the vision. But there was a snag. A crucial twist came from Lingruigi, who joined Jitamirskaya's team around 2019.
What was the problem?
Avila's original global theory, powerful as it was, had trouble with a specific mathematical trick. Often, to solve a hard equation, mathematicians look at its mirror image problem, called the dual equation. Sometimes the dual's easier to analyze.
Okay, a standard technique.
Right. But Avila's geometric object, his master key, it didn't quite fit the lock of the dual equation for the Ten Martini problem. It couldn't analyze it properly.
So they had this powerful theory, but it couldn't tackle the problem from the most convenient angle.
Precisely. It was like having the right map, but not being able to read it upside down, which was the easier way to see the path.
So what did G and the team figure out?
Jia, along with Jitamirskaya, Jiangong Yu, and Qi Zhu, found a new way to interpret Avila's geometric object. They found a different perspective on it, one that did allow them to apply the global theory powerfully to the dual equation.
They found the way to read the map upside down.
That's a great analogy. This conceptual shift, this new interpretation, suddenly unlocked the full power of the global theory for this specific hard problem.
And the result was?
The elegant finish. They could finally write a single, unified proof, not a patchwork. One argument rooted in this global theory and its geometric insight that solved the Ten Martini problem, not just for the original simplified case, but for a much more general, realistic settings closer to the graphene experiments.
So this cemented it. The butterfly wasn't a fluke, not just math. It's real, and the math explains why it's real across the board.
Absolutely. It showed that the deep, intricate structure dictated by irrational numbers isn't just some abstract description. It genuinely governs the quantum behavior of electrons in these systems.
What an incredible scientific journey from, a grad student with a massive calculator facing skepticism.
Yeah, the numerology phase.
Through decades of doubt, the 10 Martini bet, the patchwork proof, the experimental shock.
To finally arrive at this single, elegant explanation that ties abstract number theory directly to observable physics. It's really quite something.
It really is. It connects these seemingly totally different worlds.
And if you think about the bigger picture here, it just hammers home how powerful pure mathematics can be, even when it seems completely disconnected from reality.
Right.
The team behind this latest proof, they think this is just the start.
Really? What else?
They believe they found, quote, a hidden mystery behind the global theory, that this new way of looking at things will let them tackle even more complex quantum problems. It really makes you wonder, doesn't it?
Wonder what?
Well, it poses a question for you listening out there. How many other things that scientists or mathematicians today might dismiss as just, a mathematical curiosity
Mm-hmm.
or an artifact of a too simple model.
Mm-hmm.
How many of those might actually turn out to be fundamental principles governing how the universe really works?
That is definitely food for thought. Thank you for joining us for this deep dive. We'll see you next time.